can go into we are back again on YouTube. So welcome everybody for the second session of today, Thermal Physics Laboratory by Prajwalit Shikha. Yeah, please, Dr.
Okay.
Seema.
Our second session is on thermal physics laboratory by Dr. Prajwalit Shikha, Maitreyi College. It's my privilege to introduce Dr. Prajwalit. Dr. Prajwalit Shikha is currently working as Assistant Professor in Physics Department, Maitreyi College, University of Delhi. She has done dual masters. She has obtained her MSc and PhD from Vinoba Bhave University, Hazaribagh. Her field of research was based on studying the properties of heavy electron compounds. She has authored 3 books and a book chapter and published research articles in various reputed national and international journals. Welcome, Dr. Shikha. Over to you now. I stop presenting my screen. Dr. Shikha.
Dr. Shikha, please press your unmute button. You are co-host now. You can do it.
Yes, it's done.
Yeah, definitely.
You can present your screen, Dr. Shikha.
Yes, ma'am, I'm just doing that. I hope my screen is visible, ma'am.
Yes, for sure.
All right.
Go ahead.
Yeah, so good morning, everyone. Today, I will be discussing thermal physics experiments on the virtual environment. So first of all, I want to tell you that if you would look at the syllabus, then you will find out that the minimum number of experiments that are given to a particular lab is thermal lab. What is the reason behind that? So you can do only at least 5 experiments from the given list of experiments. So there is a reason behind that, because a lot of time is consumed in doing a particular experiment in thermal physics. So what is the reason behind that? So there are certain challenges in the real thermal physics laboratory which no one can deny. And what are those challenges? That there are long heating and cooling time of systems which are usually involved in the experimentation of heat and thermodynamics, and it makes the experiment very tiring and sometimes boring for the students. Also, what happens in case of error in the result? Suppose a student has performed an experiment after spending hours and hours of time in the lab, and the result comes out to be wrong. And if we tell the students to repeat the experiment, then they usually prefer to write the discussion in their files that why their result were wrong, instead of repeating the experiment. Also, it is not possible to perform an experiment with different variables because of the limited resources available in the laboratory. Also, due to long hours to perform an experiment, too many changes in different parameters or variables of an experiment seems to be little impractical. But all these challenges can be met in virtual lab environment. So virtual lab is a tool that enhances your real lab experience. What happens in virtual lab, that the heating and cooling processes that usually takes a longer time in real lab environment, here within seconds these processes occur with the same, or we can say that better accuracy, and students can repeat the experiment as many times as they wish to do without wasting much of their time, and the same experiment can be repeated with a number of variables in drastically less time. Also, since the experiment hours reduce drastically in virtual lab environment without affecting the accuracy of the result, so it becomes very practical to test the same experiment with different variables and hence develop much deeper understanding. What is the basic uh, purpose of going into the thermal physics laboratory? So the basics are that we need to understand that there are what is heating and cooling processes that are involved in nature, what how the heat is transferred from one body to the other body, how there is transformation of heat energy into various other useful forms of energy. So these are the basis of learning thermal physics and doing experimentation in the laboratory. So virtual lab is actually a boon which helps in developing all these understanding by providing various experiments, not as a whole, but you can go and search for various different parts of a single experiment, and then you can club them and you can come out with some conclusion. So here, out of all those experiments that I have shown uh, in a slide, I'm going to discuss three of them, and all those experiments I'm going to perform using a VLab from Amrita University. So the first experiment that I will be discussing is to verify the relation between thermo-EMF of a thermocouple and temperature difference between two hot junctions. What is a thermocouple and what are we going to learn in this experiment? So we are going to learn what is thermoelectric effect, which is very basis of understanding when we are switching to renewable energy sources. Here also this thermoelectric effect plays a very important role. So in this virtual environment, we are going to learn this in a very easy manner without getting bored, because a lot of variables are also available there. We can change them and we can see how the result changes. So basically, thermoelectric effect is a direct conversion of temperature differences into electric voltage via thermocouple. And what is a thermocouple? So it is an electrical device which consists of two dissimilar electrical conductors, and they have two different electrical junctions which produces a temperature dependent voltage. So this is the basic theory behind this performing this experiment that we have to understand or make students understand. How many variables are there? So as I told you that in real lab environment, too many variables, playing with too many variables is not possible. But here it's a boon because there are total 5 different kinds of thermocouple that we can work with. Here we can change the temperature of the hot junction, and we can also change the reference temperature, which is usually not required. But here we can also do some additional stuff to understand how it affects our total result, or is there any effect, is there no effect of that particular parameter. So how we are going to proceed? So for a fixed thermocouple, we have to fix the reference temperature. I'm just explaining in short what is the procedure of performing in virtual lab. There is not much difference, but here what we are going to do is that for a fixed thermocouple, first we have to select the thermocouple, then we have to fix the reference temperature to 0, and then we are going to increase the hot temperature temperature of the hot junction, and the corresponding value of thermo EMF generated due to this temperature difference at the junction will be noted down. And then there will be a graph which will be plotted between thermo EMF and temperature of hot junction, and from the graph slope can be calculated, and the slope actually gives Seebeck coefficient. So here Seebeck coefficient relates with the conversion of the temperature difference into voltage. So that is one part which is known as the Seebeck effect. So Seebeck coefficient can also be calculated by from the slope of the graph. And there's another formula that can be used, and thermoelectric power can be calculated using this formula. So these are some additional stuff that can be done from whatever data we gather after performing the experiment. So this is the graph that you will see in the VLab, where this along x-axis we plot the temperature of hot junction, along y-axis there is the generated thermo EMF because of that temperature change. And here in this graph, you can see that there are two different points. What happens as the temperature of the hot junction increases, then the thermo EMF generated also increases, and it increases exponentially. So as I shown you, this is the relation which relates that exponential variation. And then we reach a point where further increase in temperature does not change the thermo EMF. That point is called as the neutral temperature. And after when the further temperature is increased, then what happens, the thermo EMF decreases, and then we reach a point where it reverses its direction. This is called as the temperature of inversion. So we have to study this, plot this graph and study this. Now in VLab, here normally to attain this long range of temperature is usually not possible in normal lab. Also in the VLab, here whatever I'm going to perform, we will reach the point till this neutral temperature. And therefore, neutral temperature for different thermo EMF can be compared and verified using this experiment. Next part can be explained by the teacher in the lab. That is an additional thing which we cannot show in VLab. And normally in real lab also, that part normally is difficult to reach to that part. All right, so I'll just go to the simulation. Okay, just wait a minute. Sorry for this delay. Okay, so let me maximize this. I'm just trying to bring this window in the center.
Sorry to interrupt you.
Yes.
Yeah, just a minute.
Yeah. Yes. I guess this is visible now.
No, actually your PPT is shared. You have to share the screen.
All right, I'll do that. Just go to the setting and
You have to first stop presenting and then go to the present again with the screen mode.
I'm just sharing my screen. It is.
You share your screen again and share the screen, not PPT. You share the screen, please.
Yes, the screen is shared. Screen is shared. Yes.
You are on mute. Shikha ma'am, you are on mute.
Okay. But I'm not mute from my side. I guess from your side it's done. I don't know.
Shikha ma'am, voice is not coming.
No, I can hear her.
We can
No.
hear.
No, your voice is coming, ma'am.
Yes. Yes. I'm not muted.
Shikha ma'am, voice is not coming.
Voice is clear, ma'am.
Voice is
No,
clear.
Is it okay now?
Yes,
Can you
yes.
see my screen?
Yes,
now?
yes. We can see.
Sorry for the delay. Sorry for that problem. Now let us start this simulation. Okay. So here you can see that this is the apparatus in VLab, and what we can do here, we can choose different thermocouple from here, from the list of thermocouples which are available here. We have type T, type J, type E, type K, and type R. When you choose one particular thermocouple, say for example type R, it automatically displays on the screen which kind of thermocouple is this, what is the combination of the metals that are there. So it is platinum rhodium thermocouple, which is known as type R. So this is also another information that can be directly inferred. Yes, am I audible?
Yes, you are audible.
Okay.
But participants, it's a request from participants to please mute yourself.
All right. So let us quickly look at that. So we have chosen one. It's very simple to perform here. We can choose a thermocouple from the list of thermocouple that are available here. So I'm choosing here type R. So when you click on a particular thermocouple, you can see that what combination it represents. It is platinum rhodium thermocouple. Now here you can see that there are two junctions. One is the cold junction, which is at 0 degree. Another one is normally the hot junction. And because of this temperature difference only, an EMF is generated over here. Now you can see that here, other than this particular variable, we have two more variables present, which is hot temperature, and you can see that there is a reference temperature. whenever we plot a graph between temperature and the EMF, normally to get to the graph and obtain the temperature, which is the neutral temperature for a particular thermocouple, as I've shown from the graph, we have to keep the reference temperature at 0, and then we keep on increasing the temperature of hot junction, which is here labeled as hot temperature. So let us now start the experiment. Here you can see that there is a graph also which is visible below this particular diagram, and this graph is between temperature, which is in degrees Celsius, and EMF, which is in volts. And as you will start increasing the temperature, you will be able to see a graph which will automatically be plotted over here. So our reference temperature is 0 degree, and the hot temperature we can start from the left arrow key, because it is, if you are going to use mouse, then you may not be able to change it with the smallest, with the least count that is there. But if you are going to use the right arrow key on your system keyboard, then you will be able to see the variation in the smallest possible step that is designed for this particular experiment in the simulation. So now if I've increased the hot temperature to 1 degree, you can see that the voltage, the EMF generated is 0.005. It is in volts. Then let us increase further up to 2. There's no variation. You can increase 3. Now the EMF has increased, and similarly you can keep on increasing the temperature and keep on looking at the value of the generated EMF. So there is a direct relation between increase of the temperature and the EMF generated. So they can easily view this part from this experiment. Now you can, here there is one more advantage of doing it. Just normally what happens in the real lab, when we do in the real lab, it is not possible to move ahead or come back quickly. Even quickly, it is not possible to come back. Normally we have to restart the experiment, but here we have the facility, we can go back, we can move forward with whatever speed we can. It is not going to affect your output. So that is the greatest advantage of VLab that we can have in thermal physics laboratory especially. So here we are moving forward, and you can see that there is a blue line which is appearing in the graph. So just keep increasing the hot temperature. We can the rate of increase is in our hand without affecting the result. So you can see that the graph is automatically generated, and the nature of the graph, as the equation was shared, is not straight line, it is exponential graph. Now how long it will go? So there is a limitation over here. The graph actually completes with a parabolic structure, but here we will stop at the point which represents the neutral temperature for a particular thermocouple. So here, since we are using type R, so for every thermocouple, the temperature, the neutral temperature is fixed. And it is tested here, whatever neutral temperature it is representing for a particular thermocouple, it is also fixed. And it matches with the real value. So for type R, you can see I have reached to the end. It is 1768 degrees Celsius, and the graph stops over here. And this particular point, if you point your mouse pointer at any point along the graph, you will be able to see what is the value of temperature and EMF. And at the end, you can see whatever you are able to see on the screen. So this actually represents the neutral temperature for a particular thermocouple. Now the next thing is that you can quickly keep changing. Now normally we are not able to compare different thermocouples with respect to their neutral temperature, because it will take a lot of time in real lab, and even different kinds of thermocouples are not available in the real lab. But here we can quickly go to next type of thermocouple, type K, which is chromyl alumyl thermocouple. And what is the difference between the previous thermocouple and this thermocouple is, from the graph we will find out that the neutral temperature of both these thermocouples are different, and this can easily be seen in this virtual lab. So it is really a blessing to have a virtual lab especially in thermal physics lab. So now here again the reference temperature is kept at 0, and let us increase the hot temperature, and we can increase it as fast as we can. It is not going to affect the result. And you can see the graph, automatically the graph is generated, and it will stop at the neutral temperature for this particular thermocouple. Now this graph can also be, we can also ask students to note down the temperature and plot the graph. I have also done, and the nature of the graph is very similar. So the results are verified. Okay, so this is type K, which is chromyl alumyl thermocouple, and 1372 is the neutral temperature for this particular thermocouple. Similarly, for different kinds of thermocouples, the same procedure can be repeated and it can be shown to the students. The comparison can easily be shown to the students. And after doing this experiment in virtual lab, when the students go to real lab, if they get a chance to go to real lab, then they feel more excited to verify their result. Now, in this case, they have already seen that yes, this is working and it is matching with the actual value. So they go with a hope that yes, the experiment will be performed and we will be able to see the actual result. Now, another thing is we can show them with this, that if what happens, since here hot temperature range is fixed up to the neutral temperature of particular thermocouple, we can change the reference temperature and show them that what happens when the reference temperature changes. In that case, the reference temperature is representing the temperature of this ice beaker in the ice. This is the cold junction, which is at 0 degree. Now, if you're changing the reference temperature, we can show them that what happens to the voltage generated. Now, when the voltage is generated, why the voltage is generated? This is because of the difference in temperature. And what happens, there is a flow of current in the circuit, and because of that, we're able to see an EMF in this particular voltmeter. Now you can change the reference temperature, and you can show that if you're changing the reference temperature, the direction of current reverses. So this gives a fact that if the temperature of both the junctions are reversed or are changed, then the direction of current also reverses. So this fact can also be shown to the students. So all the aspects of this particular experiment can be covered in this VLab, and after doing it, they will definitely enjoy performing this in the real lab. So this is one part. Now I will be moving on to the next experiment. All right. So I guess there's no question in regard to this particular experiment. So is there any question? Then I can move on to the next
No,
experiment.
ma'am, there's right now no question.
Okay, fine. Now let us move on to the next part. So here, let me just tell you once again, one thing was missed, that this was the graph that we have obtained, and this was the point where it stopped. But we can tell the students that there is another part as well, so that can be explained to the students. And here the basic thing is to verify the neutral temperature of a particular thermocouple, and that can easily be done through this particular VLab. And also the concept of the direction of current can also be given by changing the temperature of hot and cold junction. Now the next experiment is to determine the temperature coefficient of resistance of a given coil. So for that, again, I'm going to the same. I Yes, my screen is visible.
Yes.
Yes, it's visible.
Okay, thank you. Okay, so next we're going to do the temperature coefficient of resistance of a given coil. Now, in this experiment, there are certain aspects. Let me first discuss that what we normally do in the lab, we use a Carey Foster bridge, and then we use there are two different parts of this particular experiment. The first part is to calibrate the Carey Foster bridge that we are using and to obtain the resistance per unit length of the wire. And then in the next step, we find out the temperature coefficient of resistance using this formula. Basically, in this experiment, the principle of this bridge is Wheatstone bridge is involved, where P upon Q, here you can see that this is for one arm, the second arm, then we have third and fourth arm, and there's a galvanometer. So we know that here this principle is the Wheatstone bridge principle, where P upon Q is equal to R upon X. So the same diagram can be compared with this diagram where we are using a Carey Foster bridge, and you can see that there are four gaps and different resistances are put across the gap, and this is basically the circuit. We have to obtain the null point using jockey of a galvanometer, and these are the two formulas that we're going to use to get to the value of the temperature coefficient of resistance of a given coil. The things that we can discuss here in this experiment, let me first explain the simulation, then we will come back to the things that additional things that are important and can be discussed with the students later on. So this is the first part where we are going to calibrate the Carey Foster's bridge, and then we will use that to find out the temperature coefficient of resistance of a given coil. Here in this experiment, what are the variables that are present for us? So there are basically, first of all, we can do it for known and unknown resistors. And first part, with a known resistor, we are going to calibrate this Carey Foster's bridge, and with an unknown resistor, we are going to perform the next part of the same experiment. So let me first do the first part, and the variables will automatically, you will be able to see the variables, what are the variables that are not normally available in real lab, and what you can see in the virtual lab that will be discussed while performing this experiment. So let us do the first part. We choose a known resistor, and this part is just to calibrate the thermocouple. We have chosen a known resistor, and this is the whole experimental setup, and you have to do the connections to find out the value of resistance per unit length of the wire of this Carey Foster's bridge. That is the first part. For that, let us now do the connections to do the first part. For that, the circuit diagram, you need to know what's a circuit diagram, but here there's another very important advantage of using this, that as you click on any of the part and you want to connect it somewhere, you will see that automatically you are directed towards the particular terminal where the connections can be easily made.
Dr.
Then,
Prajwalit, Dr.
yes, ma'am.
Prajwalit.
Yes, ma'am.
Sorry to interrupt you, but
Yes,
this
ma'am.
particular temperature coefficient of resistance is also being covered for tomorrow's talk. Would
Okay.
you be nice, because we are also running short of time?
All
Because
right, all
nearing
right.
12 o'clock. Is
Yes.
there any other experiment after this also which you wish to
Yes,
show?
there's a, yes, ma'am, Lee's disk experiment is there.
Yeah,
I can
kindly, I
explain that.
request you to kindly skip to that one. We'll probably
Okay.
cover this one tomorrow also. However, your
All right.
lease deck is not going to be covered by anybody else. So I would like to hear your expertise.
Yes,
on
actually, there's a problem about lease disk that when you try and open it, the simulation or the VLab using Chrome, then Chrome does not support the Flash player that has that stopped in January 2020. But if you try to open it using another browsers like Mozilla, then it opens over there.
That would be wonderful. Would you just share your Mozilla browser and show, or
yes,
somehow?
ma'am. Yes, I have already opened it. So this is
Yeah,
the Mozilla
wonderful.
browser.
That's so kind of you. Thank you so
Yes.
much.
So this is the least disk experiment. So of course, if you'll try on Chrome, you will not be able to open it.
It's
But
not shared as yet, Prajwalit, not
yes,
shared
ma'am.
as yet. I still see temperature coefficient of resistance.
Yes, ma'am. I'm just
Yeah,
going to
yeah, sure.
stop sharing.
We are greedy physicists. We try to pack everything together in 3 days. Actually, what we require is we require a week or a month to discuss.
It is good to be greedy.
Yes, greed is always good when it is in the positive direction. So we want more, and we want more. And here we have Elise.
We learn. We can't learn otherwise.
Okay. Is it now
Yeah,
visible,
yeah,
ma'am?
sure.
Okay,
Thank you,
okay.
Prajwalit. Okay.
Yes, ma'am. So this is the least disk apparatus, and I can go back to the. Is my presentation also visible? PPT is not visible.
No, PPT is not visible.
Okay.
PPT and this cannot run simultaneously. No?
Simultaneously, all right.
No, you can minimize the screen and then you can show the PPT along with this this
Or
tab.
share the whole screen. Prajwalit, stop
ma'am.
sharing and share the whole screen of your computer. Then you can have simulation in a smaller window and a PPT in a smaller window, and you can alternately enlarge and reduce. So just share the screen.
Okay. Okay, just a minute, ma'am. Not too handy with this, so I'm really sorry for this.
It's not a problem. Meanwhile, if you have questions, participants, please feel to ask. Dr. Pradosh, you asked from where these circuits can be obtained. You mean what she's showing? They are available on virtual labs, and we shall pass on the link to you. It is www.vlabs.co.in. I'm writing it out, vlabs.co.in. If you type this on the Google, it automatically takes you to the Ministry of Education of our country, and it leads you to the virtual laboratories of all the IITs and some other colleges of our country who have gathered together to make these. Do the simulations of other thermal experiments also available? No, I think Dr. Swati, she already mentioned that out of our syllabus or out of the syllabus that she displayed of DU, we hope it is not widely different from one university to another. Only few are available. Yeah, so Prajwalit, are you ready?
Is my presentation visible, ma'am?
Yeah. Additional things to discuss with, yeah. Experiment number 3.
I'll just again bother you. I'll just stop sharing this and then go back to that Mozilla. Actually, whatever sir has asked, that how many experiments are visible. So I have listed down it's on the Amrita lab, but whatever is there in the syllabus, exactly those experiments you may not find, but with little variations, the experiments are there, and you can club them and can develop the understanding which is already mentioned in the syllabus. So I am going to share that screen as well, where too many experiments from, of course, from the Amrita lab only are there, like Newton's law of cooling to find out the Stephen's constants, blackbody radiations, all those things are there, which can be easily shown to the students and understanding can be developed with respect to those concepts. So the next experiment is this Lee Charton's disk method. And as I told you that this will not open in Chrome, so you can try in another browser. And please do not, if you want to work with it, do not update it. Click the updation off so that you can continue working with it, because if you'll update it, then again it may not work in the new browser as well. So this is the actual setup in the lab, which you can see here. So there is there is this least disk apparatus. We can see that the metallic hollow cylinder is there, then below there's a thick slab, and in between these two we put the bad conductor, of which thermal conductivity is to be found. And for performing this experiment, we heat this the water in this instrument, and what happens, the steam passes through the hollow part, and then what happens, the temperature of that part rises. That heat is then transferred through this slab, through this the bad conductor, to the lower part, and then we measure the temperature, then we remove the disk, and then again we perform the experiment. So this way the aim of this experiment is to find out the thermal conductivity of the bad conductor. Now normally in the lab, what happens, we have very limited number of the bad conductors in a particular shape that we require to perform this experiment, because the shape of that bad conductor should be such that it is in contact with the whole area, so that the effective results can be obtained. So normally mica and cardboards are there available in the lab, and we can see that what other variables are there available in VLab that we can perform. So you will see this kind of setup. So this is the setup in the lab, and this is the setup in virtual lab. So you just can see that there is not much difference, and you can see that it is just the image of the real lab, you can see. So you will not find much difference in the virtual lab environment. Now here, what are the variables? Let me first discuss that, because that is very, very important part, and that is the basic advantage of using the thermal physics in VLab, because we can deal with a lot of variables. So here we can select the lease disk material. Actually in this you will find out, though it is written that you can select the material, but here only you will find out one material, which is aluminium. And then we have lease disk height can be changed, the disk's radius can be changed, and even the insulator can be changed. There are 3 insulators that we'll see, and then we can also change the thickness of the insulator. So these many variations are not possible in the real lab. Definitely we cannot change the disk height, the disk radius, because the setup is fixed. It is not possible to change, but here in VLab you can definitely change and see how it affects your result. So I'll just again go back. Take some time, so I'm really again sorry for this delay. Is the screen visible, ma'am? No, it's not. Okay. So I'm working on the Zoom for the first time, so that is why this is happening.
No
It will
problem.
not happen again.
Dr. Shikha. You take your time.
Okay, thank you, ma'am.
It's visible
Is the visible? Okay.
Yes, it's visible.
Thank you. So this is your setup. Here the procedure, as you see here, you can here click on the theory portion. You can see it is visible. Theory procedure is also visible. Then self evaluation of
is very much zoomed, so theory part is not visible.
okay, just
Yeah, there's always a time lag between the operation that the speaker does and when it is visible to us. Further lag on the YouTube and further lag on the second YouTube, which is transmitting it live.
I think it should scale it down, no? Generally, it may be.
Yeah, okay, but I'm sure, Prajwalit, you're not talking about theory in detail, right? We are running.
No, I'm not.
Time.
I just come to the VLab, ma'am. Actually, I've come to the VLab. And let me just quickly explain this. If you want me to finish, I'll quickly explain, since the variables are clearly visible, because if I'll perform it, it will take some time. So I'll just go stop sharing my screen and I'll go back to my presentation, because I'm not going to perform this, because you will be able to see the same setup in your real lab as well. And if you're teaching this, you must have worked with this experiment. So is my PPT visible?
No, not yet.
I'll just go back again.
However you hear, the best understanding is only after you do it yourself. Isn't it, Prajwalit?
Yes, ma'am. Yes, ma'am.
Yeah, definitely. So it's really an indicative. This thing is also a great thing. And with small indications, since the participants are all very learned members of physics community, even a slight indication to any one of them is certainly more than enough for anybody to gather. So we can probably. It was a tough decision to pack it up all in 3 days, and I really wished we could have 7 days. But there is this always question: how many days you can manage with the session going on. So that's the reason we are utilizing your beautiful Sunday for learning beautiful physics. Prajwalit, it is not getting shared, your PPT. And so meanwhile, as she does it, I request Ranjita to also prepare our forthcoming speaker as co-host. Yeah, here it is. Here it is. Yeah, yeah, Prajwalit, go ahead. Go ahead.
Ma'am, I'm really sorry for this
No,
technical
you don't
glitch.
have to.
And
These are
no,
technical things.
actually,
Everybody
it's first
faces.
time on Zoom. I'm just doing it, so that is why it's
It's no
getting little
problem.
difficult.
Don't feel anything. It's just everybody feels this. Okay, go ahead.
Sorry. Okay. So actually, ma'am, these things actually makes the listeners disinterested in whatever they are listening. It happens when we do with the students as well. These technical glitches, they waste a lot of time. So we have to be very careful before we are for a presentation. So I'm sorry again for that. Now again, yeah.
It's okay, dear. It's okay.
Yeah. So this is the setup lease disk that we do in the real. So I've just explained that what are the variables that we can do, and in the real lab, these variables are impossible to have these many variations in this particular experiment. So that can be done, and this is here on the right hand side. So there are two parts in this experiment. In first part, we keep the cardboard in between and start the experiment. In the next part, we remove it, and this is the next part that looks like. So in the first part, what happens, we start the temperature, it starts heating, and then both the temperatures, here you can see that the thermometers, they come to and the constant temperatures. And after it happens, then what we do, we again remove the cardboard, and we start again cooling it down from the temperature, from the constant temperature. When it comes above 10-degree rise, then from there we start cooling it down. And then here is the main process, that we keep noting down the temperature and the corresponding time, and the time and the temperature graph can be plotted. And this is the graph that you can see here. And from this graph, the temperature, here we can find out what is the temperature coefficient of this particular slab. We can do that, and thermal conductivity of the bad conductor, and the coefficients can be calculated using this formula. Now the next thing is that it was the thermal conductivity. Now the question here is that thermal conductivity, is it a constant? Because we know that there are different variables, there are various materials, but for all those, the thermal conductivity is supposed to be a constant value. But is it really a constant? So for that, we can always change the variable. So to develop that understanding in the students, that whether thermal conductivity is constant, we can change these variables, which we cannot do in real lab, and show them and let them conclude that what result do they come out. Is it constant, is it variable, and if it changes, by how much amount, and on what factors it depends. So normally in the equation, it is clearly visible that there are various variables in the right hand side. Yes. So this is one thing that can be asked from the students, and that is the extra thing that can be done with the students with these variables. Now, this is the link where you can go and find out the list of experiments. Now, when you will type on the browser a virtual lab for a particular experiment, then you might find two different kinds of windows. Now, in one window, set this kind of experiments you will be able to see. In the second window, you will see such kind of listing. Now, both are actually two different things. If you'll click on this left hand side window, then you will only be able to see the simulation, the VLab simulation, and the theory and procedure parts will not be visible to you. So it might be difficult to proceed if you are not able to see the theory or procedure. Then you have to click on this link I have already shared. So if you click on this link, you will be able to come to this particular page, where if you are going to click on any particular experiment, you will be able to see the complete window with theory, procedure, simulation, and all that. So this is it. And these are different experiments like heat transfer by radiation, conduction, natural convection, phase change, black body radiation, Newton's law of cooling, all these things you will be able to see. So these are two different videos. The list of experiments, you might find it different, but I've just shown you to tell you that you may find out only the simulation window if you're typing VLab simulation for a particular experiment. But you want this kind of window where when you're clicking it, you are going to see the complete window where theory and procedures are also visible. So thank you. This is it.
Thank you, Dr. Shikha, for such a nice presentation on thermal physics lab. I myself also take thermal physics lab, so it is very interesting to watch thermal experiments online. By simulation, we can overcome many limitations that we face in actual lab actually.
Yes.
So thank you so much.
Thank you.
So if you
Thank you, Dr. Prajwalit. Indeed a pleasure.
Thank you so much, ma'am.
I think it is really wonderful that you did it quite quickly and adjusted the time accordingly. I'm really thankful to you for that.